In this section of Chapter 4, we are going to be talking about ring structures. So first off with our rings, we have a little bit of strain that we have to talk about with our rings. One strain is going to be just that, it is ring strain. And this is going to be due to the geometric constraints of the ring itself. When we start to take those carbons from the straight chain and we start to cyclize them, we're going to see that that cyclization has a strain associated with it. The reason for this strain is because we lose the freedom of rotation within the bonds themselves. Once we get into that confined ring, we can no longer have freedom of rotation around the double bond because we can't cycle atoms inside of the ring and bring them back out. So we lose that freedom of rotation, which is what helps to generate some of this ring strain. We can actually quantify the amount of ring strain that we have based on heats of combustion. And your textbook goes through quite a bit of calculations associated with determining ring strain based on heats of combustions. You do not need to know any of those values, and you do not need to be able to calculate those values for me. Just recognize that we can actually quantify, once again, this ring strain based on heats of combustion, which is basically heating up our sample to break that ring apart is what we would be looking at. When we talk about rings, there are certain numbers of rings that are more stable than others. We're going to see through this chapter that our 6-membered rings have the lowest amount of ring strain. They tend to be the most stable size of a ring. If we look at 5- and 7-membered rings, they have very low ring strain, so they tend to be fairly stable structures when we talk about 5- and 7-membered rings. Many of our other rings, less than 5 or greater than 7, tend to have higher ring strain. So oftentimes those rings don't tend to be as stable. There are some rings that we really can't form very readily either because there's such a high ring strain associated with them. The stability drops significantly when we look at those sizes of rings. It's not saying that we can't form them. Sometimes we can under certain conditions, but oftentimes they're not very stable or they are going to be very reactive. So the first ring that I want to look at is going to be that cyclopropane ring. So this formula is going to be our C3H6. When we look at this structure, it is going to be 3 carbons, and they are going to be all in a ring for us. With this structure, all of those carbon atoms are sp3 hybridized, meaning they all have 4 bonds associated with them. They all have that tetrahedral nature. So if we actually plug all of our hydrogens on here, since all of our carbons are in the same plane, that means that all of our hydrogens are either going out of the plane or they're going back behind the plane. So if we look at this structure, all of those angles within the ring itself, those carbon-carbon bonds, are approximately 60-degree angles, and all of those carbons are in the same plane. That makes all of those hydrogens eclipsing. So if you'll notice with that structure, all of those hydrogens are going to be eclipsing for us. Which we already know from our previous session creates extra strain within our molecule with those eclipsing hydrogen atoms. So overall, this molecule has significant strain from us. It has strain due to the variance in angles from the tetrahedral 109.5 to the 60-degree angles that we would need to make that cyclopropane ring. And we also see that everything is eclipsed. If we actually look at my model kit, I can't even generate and make my model kit form that 3-membered ring because of the angle strain that is applied there, which is where our angle deviates significantly from the angle that we have based on the shape of the atom. So we can't even really make this with my model kit. It's a very unstable structure when we talk about cyclopropane. The next one I want to look at is going to be cyclobutane. If we have all of our carbon atoms in the same plane, we run into the same issue that we did with our cyclopropane. Here the bond angles would be 90 degrees between those carbon atoms. All of our hydrogen would once again be eclipsing. So we have a very non-stable structure again with a lot amount of strain associated with it. So what actually happens here in this structure so that it relieves a little bit of that strain is it's going to adopt what we call a puckered shape. With this puckered shape, two of the carbons are going to be in a different plane than the other two carbons. So I'm going to kind of draw this nice little puckered shape. So you can kind of think about it as those two carbons in the middle are higher than the carbons that I have on either end. What this does for us is it also allows us to take some of the hydrogens and make them non-eclipsing as well. So we can have hydrogens pointing out here, and then these hydrogens would both be going back behind the plane of the screen. The hydrogens on those corner ones would be in the plane of the screen as well. So if it adopts this puckered shape, and I can make this a little bit with my model kit, if it adopts this puckered shape where those two carbons in the middle are higher than what they are on the ends, you can see that my hydrogens are no longer eclipsing. If we look down some of those bonds, you can kind of see that staggered notation between those bonds, which then allows us to get rid of some of that strain that we have. So instead of everything being nice and planar for cyclobutane, it adopts this puckered shape for us. There still is some significant strain in this puckered shape. The angles are about an 88-degree angle, so we're still not close to that 109.5 that we need, but we do alleviate some strain because of the we no longer have all those hydrogens eclipsing each other. But overall, we have not relieved enough strain for this molecule to really be considered stable for us. So this is still considered a non-stable ring form when we just have the 4 carbon atoms. The next one I want to look at is going to be that cyclopentane ring. So this is our C5H10. Once again, if everything is actually planar, which is the way we typically draw it, but if everything is planar, we run into all the same issues. Our bond angles are not near what they need to be for the tetrahedral shape. All of our hydrogens are going to be eclipsing. So we still have some issues if everything is planar. So what this adopts is it does adopt a puckered shape. What we oftentimes call this is an envelope shape, where one of the carbon atoms will be out of the plane and the other 4 carbon atoms will be in the plane. So what this does for us, once again, because of that puckered or envelope type nature, we do get rid of some of the eclipsing hydrogens. We don't get rid of all of them, but we do get rid of a few of them when it adopts this envelope or this puckered type shape that we have. We do alleviate quite a bit of strain here because our bond angles go back to being very close to that 109.5 because of it. So if you actually look at my model kit, it's not very planar. If I put it on the side, one of those carbon atoms is sticking out significantly compared to the other ones when we look at it. That is what we call about this envelope, this puckered shape that we have. So if we actually look at it more flat like this, we can see that that alleviates all my hydrogens being eclipsing. We still do have a few that are going to be eclipsing, but they're not completely eclipsing because of the shape that we have with that puckered nature. So it alleviates quite a bit of our strain, and all the angles are that 109.5 angle. You'll notice in my model kit there's no bending of the bonds. There's nothing keeping those bonds any different. That 109.5 degree angle is pretty stable in this envelope type form for our cyclopentane, which is why we significantly lower any of the strain that we have in this ring. So it becomes a much more stable ring for us. It's not the most stable of a ring that we can have, but it is going to be a stable ring, a much lower energy ring. The last ring that I want to talk about is going to be the cyclohexane ring. With our cyclohexane ring, we run into the same fashion. If it is planar in nature, which yes is the way that we typically draw it on paper, but if it were planar, we would see once again all the hydrogens eclipsing. We would have a lot of strain associated with this structure, but it is the most stable form that we have. So what cyclohexane does is it does adopt 2 forms for us that allow it to have the stability that we need and lose most of the strain that is caused due to rings. One of the adopted forms that it has is what we call the chair form. So in our cyclopentane ring, we had 1 carbon higher and then we had the 4 in the plane. What we're going to do with our chair conformation is we're going to do almost the exact same thing. We're going to have 4 carbons that are in the plane. We're going to have 1 carbon pointing up and 1 carbon atom pointing down. which you kind of think about this if you're lounging at the beach. Hopefully you see a nice chair there, which is where that form name is coming from. It is our chair form. So we have 4 carbons in the plane. We have 1 carbon pointing up, we have 1 carbon pointing down, and this allows us to maintain the 109.5 degree angle that we need for those tetrahedral carbons, and it also allows for the non-eclipsing hydrogens that we need in order to cause some stability as well. With the chair form, what we do see is what we call a ring flip. You'll notice that one of the carbons is up, one of the carbons is down. I can easily draw it the other way, and that's what we call the ring flip, where I'm going to point the opposite carbons up and down. So this is what we would refer to, and we will start talking about in terms of a chair flip or a ring flip. With all of our hydrogens, if we draw some of them in for you, our hydrogens are no longer going to be eclipsing for us. They are going to adopt that staggered conformation. Hopefully you'll notice as I am drawing them in, I'm alternating what is pointing up and what is pointing down. That is what has alleviated our torsional strain, or that eclipsing strain that we have as well. When we get ready to do that ring flip, we see the same type of notation in terms of the hydrogens, that they're still going to be in that non-eclipsing format that we have. So I'm just going to go ahead and draw in all of these hydrogens. While I am doing that, I will tell you right now, we do get very picky with our chair conformations in organic chemistry. Chair conformations can talk and discuss with reactivity of molecules. It can define for us stability of molecules. So you want to get very, very comfortable with drawing these chair structures. Your textbook walks you through some hints on how to draw chair structures, but you do want to get very, very comfortable with drawing the chair structures. And what they look like, and the orientations of all of those hydrogens, which here soon will also become substituents as well. So I encourage you to practice them. On exams, if chair structures are drawn incorrectly, you will not receive full credit from me. So please practice drawing these chair structures. With this interconversion here is very, very fast, or this ring flip is very, very fast. There's only about a 10.8 kilocal per mole energy difference to actually go through this chair flip. So if we're actually looking at our molecule, it's constantly going through what we call this pseudo rotation, or this chair flip when it is in solution. We'll look at it here with the model kit very quickly for the chair. So I have my 4 atoms that are in a square here. Those are all going to be in the same plane. I then have 1 carbon atom pointing up, and I have 1 carbon atom pointing down. So then when I get ready to do my chair flip or my ring flip, I'm just going to flip the carbon atoms that are pointing up and are pointing down. It kind of alleviates then, if we turn it on the side, you'll notice that nothing is eclipsing. When we actually look at our hydrogens, they are all staggered when they are in this chair conformation, which is why it is the most stable ring that we will talk about. So because of the different positions that we have in our chair conformation, we do have 2 types of positions that we're going to see for our hydrogen atoms. So if you remember when we were drawing our chair structure itself, we had the 4 carbon atoms that were in the plane, we had 1 that was up, and then we had 1 that was down. And because of that, when we actually get ready to put in our hydrogens, the hydrogens have different positions in their directionality in relationship to the carbon atoms, or to the chain. So if I walk around with each one of my carbon atoms, I'm going to have hydrogens that are pointing directly up and are pointing directly down. They are on this nice vertical axis compared to the chair itself. So all of these ones that I have drawn here, and I'm going to leave them in red, these are what we refer to as the axial position. They are perpendicular to the chair itself. They're straight up and they're straight down. And if you've noticed, as I've gone along all the carbon atoms, they alternate the direction they are pointing. It's pointing straight up, the next one is pointing straight down. It's pointing straight up, the next one is pointing straight down. And these are what we refer to as our axial positions. The other position that we have is going to point in the opposite direction, but it's going to be on a diagonal. So I have a diagonal down, I'll have a diagonal up, I'll have a diagonal down, diagonal up, diagonal down, and diagonal up. So you'll notice the ups and downs are opposite of what those axial positions were, but everything stays on a diagonal so that we have that tetrahedral shape. So the purple that I have there, these are what we call the equatorial position. So you'll want to get used to these positions and the terminology associated with these positions as well. So once again, if we actually look at our kit that I have here, I've got my kit drawn, I've got my 4 that are in the plane, I've got my 1 pointing up, and I've got my 1 pointing down. The ones that I have blocked off in white, those are all the axial positions. They are either pointing straight up or they are pointing straight down. Pointing straight up, straight down, straight up, straight down, and it kind of walks along our ring in that fashion. The other ones that I don't have the white spheres on, those are the equatorial positions. They're diagonal, and you'll notice they're in the opposite directionality. So here's my axial straight down, here's my equatorial up, but it's at a diagonal. Here's my axial straight up, here's my equatorial down, but at an angle. These positions are once again going to become important as we start talking about stability of cyclohexane rings and as we start putting substituents on these cyclohexane rings as well. But then what we have to pay attention with is we do have to do a chair flip. So remember those ring flips, those interconversions are very rapid. They are very, very fast. So if I draw my chair or my ring flip, what was pointing up is now pointing down. What is pointing up, down, is now pointing up. So what that means for us in terms of the axial and the equatorial position, I can't change the face that things were on. So you'll notice my red point here, so we'll label this as carbon atom number 1. And carbon atom 1 is now pointing down as well. So I'm not going to change the numbering, I'm not going to change anything about the carbon. All I did is I just flipped. So from here, the axial position that was pointing up still has to be pointing up. But now because that carbon is facing down, it is in the equatorial position, where the purple that was in the equatorial position and was pointing down is now in the axial and it is pointing down. So what we're going to see when we do our ring flip is we see a change in the positionality. On this other side, now my purple becomes the axial position and my red becomes the equatorial position. So we see a change in them. So I can continue to walk along with my hydrogens. So I have my hydrogen pointing straight down. My next one is going to point straight up, straight down, straight up, straight down, and straight up. What were now my axial are now my equatorial. So my first one I have up at a diagonal. My next one will be down at a diagonal, up at a diagonal, down at a diagonal, up at a diagonal, and then down at a diagonal. So again, we see a flip in the positions that we have. Again, while you are learning to draw your rings, you also want to learn how to draw and label these axial and equatorial positions. Once again, in order to receive full credit from me on anything that is hand-drawn, you do need to show these rings appropriately. So I do want to show you back in my model kit. So here's my model kit with the original chair that we have, where all my axial positions are the ones with the white spheres. I'm now going to do my ring flip. So I'm going to bring this one down. I'm going to bring this one up. And hopefully you now have noticed that what was all axial is now equatorial with those white spheres. So we change positions when we change our ring flip. One more time just so that you can see it. Here was the original ring that I had on my structure. Where all of the white spheres are in those axial positions. They're either straight up or straight down. When I do my ring flip, all those white spheres are now in the equatorial position. So again, you want to get used to understanding that rotation, pseudo-rotation, that flip-flop, and how to draw all of these chairs as well. So another thing that I want to look at with this chair conformation to kind of help understand the stability of it is to look at this with our Newman projection. So remember with our Newman projection, this is where we look down our bonds. So what we're going to do with our Newman projection is we're going to take our chair conformation that we just had And I'm going to rotate it, and we are going to look down the carbon atoms that are all in the same plane. So that's what we're going to do for our Newman projection, is we're going to look down the carbon atoms that are in the same plane. So we'll have one on the right, and remember our dot is for the carbon atom that is in the front. I will have a circle for the carbon atom that is in the back. So if we look at this, we can say that this is this carbon here in the front, and then I've got the carbon in the back. If you'll notice with this carbon in the front, it goes up to what is the carbon that is making my ring. There is a hydrogen pointing out, which right now has the white sphere on it. There is also a hydrogen pointing straight down for us as well. If we then focus on this carbon atom that is in the back, it is pointing down to the other carbon atom that is part of the chain. It has a hydrogen atom that is straight up, and it has a hydrogen atom that is going out. So that's the white sphere that's going out. The non-white sphere is the one that is going straight up in that axial position. So from here, then I would look at the other two carbons on the other side. So carbon atom in the front, carbon atom in the back. The carbon atom in the front is what is going up to that other carbon atom. It then has a hydrogen pointing straight down without the sphere. It has a hydrogen pointing up at a diagonal with the sphere. So this is the carbon we'd be looking at, straight down and out as a diagonal. The one in the back is the one back here, so it is going down to the other carbon of the chain. We have a hydrogen pointing straight up in the back. It's this one back here without the sphere on it. We also have one that is pointing down and at a diagonal. So if you look at our Newman projection here, everything is nicely staggered, which is again one of the rationales for why our cyclohexane ring is so stable, because no matter how we rotate this or what carbons we look down, because of that chair conformation, we have a very stable conformation with all of our hydrogens being staggered. The other conformation that our cyclohexane can adopt is what we call the boat structure. So for the boat structure, what we're going to do is we're going to go ahead and keep all four of our hydrogens in the same plane. I'm going to go ahead and angle one carbon up, and I'm going to angle the other carbon up as well. So hopefully you can see a nice little canoe here, a nice little boat that we have. With this, it is not as stable of a form as what the chair form is, because we do have eclipsing hydrogens. So these hydrogens that are all on the plane, because the two carbons on either side are going up, they are eclipsing hydrogens that we will see there. The other issue that we have are going to be that both of these carbon atoms are pointing up. And with their hydrogens, we see or can see, especially if these are things other than hydrogens, some repulsion factor here. We refer to this as being a flagpole interaction because those two hydrogens are up on top. They're very close to each other, which again causes some interactions that we're going to be looking at. So if I take my kit and instead of looking at it in that chair conformation where we have one carbon down and one carbon up, I'm going to point both of my carbons up. So now I have that nice boat shape. We could flip it, make it an upside down boat, but we look at it in this fashion to describe it as being a boat. So you'll notice up here that my hydrogens up here at the top are very close together. We have a lot of interaction between them. If we look down those carbons in the plane, what you will see is everything is eclipsing. My hydrogens are in the same plane, both pointing down. I've got hydrogens in the same plane, both pointing up as well. So let's look at the Newman projection. Again, looking down those carbon atoms that are in the same plane. So we have our carbon atom in the front. So we have our carbon atom once again in the front. We have our carbon atom in the back behind it. That carbon atom that is in the front, we have it going up to the CH2 that is part of the ring. We have a hydrogen pointing out and up, and we have a hydrogen pointing straight down. So there's my hydrogen out and up with the white sphere and then pointing straight down. The one in the back has the exact same connotation. It is going up to a CH2 unit. It has a hydrogen coming straight down. It has a hydrogen going straight up. If we then look at the carbons in the plane on the other side of our structure, the one in the front going up to the carbon, hydrogen pointing straight down, hydrogen pointing straight out. The carbon in the back is exactly identical. So you will see here that everything is eclipsing. So it is a high energy form for our chair structure, but it is a form that we will see our structure rotate through. So remember, we have what we call that pseudo rotation of the rings going back and forth. This boat is one of the conformations that is a common conformation we will see as it rotates back and forth. So remember, we had an energy barrier for that rotation. This boat is kind of one of those barriers why we see some energy differences as we go from one chair conformation into the other chair conformation. As we interconvert between those two chair structures, there's a couple other things that you want to be familiar with that we can rotate through. These are both higher energies than even what the boat would be, and this is our twist structure. In our twist structure, it is just that. We're going to take our 6 carbon atoms and we are going to twist them together. So this is our twist structure. What I do want to point out for you is we still only have 6 carbons in this structure. I've got 1, 2, 3, 4, 5, and 6. What this structure is trying to denote for you in our twist structure is that one of those bonds is in the front and one of them is in the back. So this one that I have drawn with the straight line and no gap in it, that is really the bond that is in the front that you're looking at here. The one that I have drawn back here with the gap is behind that bond in the front. So it's kind of putting some three-dimensionality into that twist that we see. And again, with that twist, so here's the bond in the front, here's the bond in the back. So we leave a gap for that bond in the back, so there is no carbon atom there. If I were to draw it without that gap, you would think that this was a carbon atom here, and it looks kind of like a bow tie. You want to be careful and stay away from those bow ties when you're drawing any of your structures. That's not a carbon atom there, which is why we leave the gap to denote that one of the bonds is in the front and then one of the bonds is in the back. And this is what we refer to as the twist. It's another high energy species that our chair conformation will go through as it interconverts between one chair and the other.